Hi, welcome back to Basic Logic and Open Introduction. I'm Dr. Nick McGinnis. We are now doing part 2 of Chapter 7 of For All X, the Lorain County remix, the open source textbook you can freely download in order to follow along with this course. Now, in the last video, we started using truth tables to prove properties of sentences, semantic properties like something's being a tautology or a contradiction. The next thing we're going to look at are semantically contingent sentences. Roughly, those are sentences that could either be true or false, depending. Sentences that are not tautologies nor contradictions. They're going to have some rows true and some rows false underneath the main logical operator. Most sentences of SL are going to be contingent. That is, most sentences are going to be sometimes true, sometimes false. Of course, I say most, but really, there are infinitely many tautologies and infinitely many contradictions in SL, and infinitely many contingent sentences. So, strictly speaking, sort of that's wrong. However, in the wild, as it were, if you were to construct random grammatical sentences of SL, chances are they're going to be contingent. Now, when I say that there are infinitely many contradictions in tautologies and sentential logic, you might say, well, that doesn't sound right. But it's true. Well, one interesting exercise you might do, going back to this notion of recursion when we define the syntax of SL, is whether or not you can provide a way, a recursive generative algorithm to generate tautologies, contradictions, and contingent sentences in sentential logic. What I want you to do is to stop and write down instructions to build sentences that are recursive such that it would yield infinitely many sentences of the appropriate type. For example, a contradiction. So why don't you pause the video and think a little bit about how to create a recursive algorithm to yield new tautologies and contradictions. Did you work on it a little bit? It's actually, to me, a really interesting question. You have to think a bit about what are the properties of tautologies and contradictions. Mind you, I didn't ask you to provide an algorithm giving me all possible tautologies and contradictions. Merely what I want is an algorithm that would give me an infinite set of contradictions. So, for example, do I have a, okay. So, for example, one nice way of generating tautology would be by starting with a tautology and then finding a way to generate new ones. So you can start with a seed tautology. So here's my algorithm. If P, then P is a tautology of SL. How can I generate a further tautology from this? So, and if choose like metavariable Q is a tautology, then if Q, then Q is a tautology. And actually, we're done. So it might be a little bit cheating up here to say, I'll stipulate my tautology. But of course, we did it with our recursive syntax originally. We say atomic sentences are state sentences of SL. So I'm going to say, if P, then P is my seed tautology. And for any Q which is a tautology, such as this one, then if Q, then Q is a tautology. What is this going to look like? If P, then P, then. So the sentence is going to look like this. If P, then P, then, if P, then P. But now if this is a tautology, then of course, I can just iterate the process again, make a big bracket, and just keep going. Now I have a longer tautology. So now I've generated infinitely many tautologies. By this way, I can also generate infinitely many contradictory sentences. So it's actually simpler than the question initially seemed. And we can kind of informally prove that a recursive algorithm like this would always work. I could, for example, assume the opposite and derive a contradiction, which is what I've done 2 times already in the last videos. So if I have a informal reasoning here, if Q is a tautology, then if Q then Q must be also a tautology. Well, I could say if Q is a tautology, it's always going to be true. Now, suppose that this wasn't going to be a tautology because it has a value false. Let me just make the video big again. There we go. Now, if this were going to be false, then Q would have to be false in order to get true, false, false. But we've already said Q is true, so it can't take two different values. So if Q, then Q must always be true, given that Q is a tautology. So for any given Q is a tautology, if that tautology, then that tautology will itself be a tautology. I can prove it informally. Therefore, I know my recursive algorithm works. Fun. Logic is fun. You're having fun. You don't regret watching 6 hours of logic videos. And I don't regret being in a classroom on a beautiful summer day doing that. I don't. Okay, let's move on to logical equivalence. I'm going to leave creating a recursive algorithm for contradictions and contingent sentences to you. Of course, a contingent sentence, I didn't spend a lot of time on it. Just for a refresher before we move on to logical equivalence. A contingent sentence is a sentence where underneath the main logical operator there's some T's, some F's, right? In other words, it's neither a tautology or a contradiction. Build the truth table, main logical operator, some T's, some F's, contingent. Done. Not even going to give any examples. Why? Because logical equivalence is more interesting. Two sentences are logically equivalent, semantically, in sentential logic if their main logical operators have the same truth values on every row of a completed truth table. This is a slightly more complicated definition, right? You have to do two truth tables, look underneath, and see that they're the same. But there are other ways to think about equivalence. For any two sentences in SL, they're going to be logically equivalent if the sentence P, if and only if Q, is a tautology. Bonus question, is there a way to define equivalence in terms of contradictions in a tautology? Yeah, sure. The negation of the biconditional is a contradiction. Ding! So logical equivalence in SL can be thought of as kind of an intertranslation. Any two sentences that are logically equivalent mean the same thing and can always be replaced with each other. And won't change anything about the set of sentences. It won't change their consistency. It won't change whether or not a set of sentences is a contradiction. And importantly, it won't change the validity of an argument. So I can replace sentences in an argument, premises of an argument, with logically equivalent sentences, and it won't compromise the validity of the argument. That's going to be actually pretty useful to us. So here are some sentences that are, in fact, logically equivalent. Now you can prove it by either method. You can make two truth tables and show that underneath the main logical operator they're identical, or you can show that their tautology, that their biconditional, is a tautology. All right, so pause the video, work on that. I keep looking over there because there's someone in the hallway. You pause the video. I'm going to have a drink of my protein smoothie. All right, let's do a couple of these. I'm not going to do all of them. These videos get too long. How about we start with if P then Q is equivalent to either not P or Q. Now, I told you these are logically equivalent, and I don't believe in trick questions. So in particular, you know that they're equivalent. It's just up to you to prove them. So let's do a couple. So here's this. All right. So we have if P then Q, and either not P or Q. Are they equivalent? Well, let's do the first way. Let's do both truth tables. I'm going to do the full truth table, even though, of course, this is just your regular conditional. You should be very familiar with it at this point. True, 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 false, 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 true, true, false, false, true. It's just your regular conditional truth table. It's only false in one case. Just rewrite that F so it is a bit more visible. So this is the main logical operator. This is the one we're going to be interested in checking. Now we're going to want to be consistent here and make sure that the P and Q has the same values here. So we have true, true, false, false, true, false, true, false. So what do we do here? What's the next logical operator in line as we complete this truth table? Is it the OR? No. The OR is going to get its values from Q and negation. It's not P. It's either not P or Q, not neither P nor Q. So what does the negation do? It takes the T's, flips them to F's. It takes the F's, flips them to T's. So we have false, true. True. It's a disjunction. The disjunction is only false in one case, when both of the sides are false. False, true, true. False, false, false. True, true, true. True, false, true. So are these the same? Is this column same? That column, true, false, true, true. Yes, so they are in fact logically equivalent. Now, one question I get asked sometimes is, are they logically equivalent if we have different atomic sentences? For our purposes, we're going to say no. So it might be that if I have like not B or C, is that logically equivalent to a P then Q? No, because the atomic sentences are different. Either not B or C is equivalent to if B then C. But got to remember, these aren't necessarily metavariables. These are the atomic sentences themselves. Okay. Now the next step here, why don't we just quickly do it the other way I suggested, which is to prove the tautology of their biconditional. So let's put big old brackets on either side here and add a sentential connective, the if and only if, which is the double arrow. Now, just to refresh your memory, the if and only if connective is true when both sides have the same value and false when both sides have two different values. Okay, why don't I write it over here since there's a little bit of room. P biconditional Q, true, true, false, false, true, false, true, false. Is that more or less legible? True, false, false, true. Should be able to just snap out, oh, I'm back in frame, be able to just write these truth tables out every time, right? Same value, T, 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 different values, true, false, 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 true, false, same value, false, false, then true. Right, which is exactly what you want to see. When they have the same values, it outputs true, i.e., this is what we want for testing equivalencies. When they have the same values, we want them both to come out true. We want the connected to come out true, because they have the same value, which is exactly what logical equivalence tests. So, let's see here. What values are going to serve as input for this one? For this biconditional, it's going to be the if here and the or there. So true, 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 false, false, true, 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 true. Now why is that? Of course, well, we have a nice tautology, a nice column of all truths here. Why is it a tautology? Why? Because they have the same truth table, and because they have the same truth table, their values are always the same, which is exactly what the biconditional asks. The biconditional outputs true when the values are the same on either side. So we have a nice tautology underneath the main logical operator. Notice that, suppose I put a giant negation and two more giant brackets here, denying the biconditional of logical equivalent sentences yields a contradiction. Why? Because all these truths are simply going to be flipped to F's. Right? So all of this column here is going to get flipped to F's. So the negation of the biconditional between two logically equivalent sentences is itself a contradiction. So if I say it's not the case that P and Q, if and only if either not P or Q, that's a contradiction. If I deny the logical equivalence, I generate a contradiction. That's pretty interesting. So we see that all these kind of semantic properties, being a tautology, contradiction, logical equivalence, they're actually very subtly interrelated using truth tables. You can all prove these things. Logic is awesome. Right, what about some of the other examples? Now that you know how to do them, I encourage you to sit down and actually work through them. Show that all these sentences are in fact logically equivalent, even some of the unobvious ones. All right, pause the video, get out some pen and paper, and work on them. Because I'm not doing them. Okay, moving on. Did you pause? Did you do it? Okay. Consistency and validity are the two next topics. Consistency we're going to just kind of do really quickly. A set of sentences is consistent if and only if there's one row of the truth table where all the sentences are true, and they're going to be inconsistent otherwise. Their conjunction will be a contradiction. So there's a set of sentences here, either P or Q, if P then Q, either not Q or not P. Are these three sentences consistent? Is there at least one way in which all these sentences are true simultaneously? There is one such value assignment. I just did a shortened truth table here, right? So if this is true, 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 right, when P is equal to F and Q is equal to T, right, P is false, Q is true, all these three sentences are true at the same time. So you could do the full truth table, in which case you just need to find one row where all the sentences are true simultaneously. If there's no such row, then the sentences are inconsistent with each other. Why don't I just do the full truth table for the first two of the sentences in the set. Let's erase all this. So suppose I'm just interested in the first two sentences here in my list, and I ask you, is saying if P then Q consistent with either P or Q? That's a good question. So we're going to go true, true, false, false. True, true, false, false. It's the same P as far as I'm concerned. True, false, true, false. True, false, true, false. True, false, true, true. True, 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 false. All right. Now, are these logically equivalent? No. They have different main logical operators, and they're biconditional and obvious tautology. However, these two sentences are consistent with each other, because there's at least one row, and there's in fact more than one row, where the sentences are true at the same time. So is it consistent to say both these things? Sure. If P then Q is consistent with either P or Q, in the case where both of the atomic sentences are true. So the sentences are consistent. So it's a really easy proof. It's a really easy check. All right. Now let's finally get to validity, the most important of our concepts. And I just dropped my marker. I'll be right back. Hi. I can give this neat kind of semantic definition using the truth tables. Now, I keep saying it's semantic as opposed to syntactic because validity here is not a function of the grammar of how I'm constructing these sentences. I can't just look at the way I constructed these sentences and give you proof right now that the sentence, the set of sentences or the argument is valid. I can give you a semantic argument. It's semantic because it depends on the truth table's kind of interpretations of the sentences. That's why I keep saying a semantic definition. Because, right, it's not a function of the recursive definition of how I'm going to construct these sentences. It's a function of this kind of like meta-linguistic talk about an argument is valid if there's no row of completed truth table, right? None of that stuff that's not syntactic. That's me talking about properties of the sentences in a natural language. All right, parenthesis closed on that topic. An argument is valid when there's no row of a completed truth table, such that all the premises are marked T and the designated conclusion is marked F. So let's suppose for a sec, right? So let's just do this again, where there's no row where all the premises are true and the conclusion is false. Now I have on the board two consistent sentences. Now suppose I pretended that this was premise 1 and this was my conclusion. I was saying, look, if P then Q, conclusion either P or Q. Is this a valid argument? Well, the question is there a row where the premises are true, in this case there's only one premise, and the conclusion false? Sure there is. True premise, false conclusion. So this, if I had an argument that went like this, premise 1, if P then Q. Conclusion, either P or Q. That's actually not valid because we can have true premises, and a false conclusion. It sounds like it should be valid if P then, if it's raining, I'll have my umbrella. Therefore, either it's raining or I have my umbrella. Wait a minute, that's actually not valid. So how did I find out? There's a row where the premises are true, but the conclusion false. Another way of thinking about it would be for any set of premises, P, Q, however many there are, and some conclusion R, an argument would be valid if and only if the sentence I've given here is a contradiction. That sentence is roughly like this. It's the premises in a conjunction with a conditional. So if premises, then conclusion is a contradiction. Well, the negation there. If the sentence, not the case that if premises, then conclusion. If that's a contradiction, then it's valid. In a way, this is interesting, the conditional mirrors the concept of validity at the truth table level. Right? When is a conditional false? When the antecedent is true, but the consequent false. And that makes the conditional false. But validity kind of operates the same way. An argument is valid in every case except one case, when the premises are true but the conclusion false, which kind of mirrors the conditional. So this is going to be like a really important kind of link up between this higher order semantic concept of validity and the definition of the truth table. Sorry for the bad cut there. So let me actually do that with the argument we have on the board already. Let's look it up here. So here we have a conclusion if P, premise if P then Q, and a conclusion either P or Q. Suppose this is an argument. My argument is premise 1 if P then Q. Therefore, I'm concluding conclusion either P or Q. Is this a valid argument? Now, we already know it's not a valid argument. There's at least one case where the premises are true and the conclusion is false. Now, because I said the conditional sort of mirrors the concept of validity, what we would expect in a valid argument is that if I put a conditional here, I get a tautology, and its negation would be a contradiction. But is it a tautology? So, if premise, then conclusion. True, 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 false, true, 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 false, false. So it is not a tautology that if premise, then conclusion. Likewise, if I negate it here, I won't get a contradiction. In other words, it's not contradictory to deny that if premise, then conclusion. Right? So the conditional informally mirrors validity, so I can verify validity using a truth table. I can do it two ways. I can see if there's a row where the premises are all true and the conclusion is false. Or I can take the premises, then make kind of we only have one premise, but if we have many premises, we take all the premises, put them together with and statements that say premise if, premises, then conclusion. And we say, is that a tautology? If it is a tautology, it's a valid argument. Or if I put the negation, take an extra step, right? If it's a contradiction to deny it, then it's also a valid argument. In this case, it's not, because it's not a tautology and its negation is not a contradiction, right? I don't contradict myself by denying that if premise then conclusion. Cool. So, should we try it again with some different arguments? Sure. So, here's another example. We have two premises and a conclusion. The premise 1 is, if not L, then either J or L. Premise 2, not L. Conclusion, J. So is it possible to have true premises and a false conclusion? No, the argument's valid. Whenever the premises are all true, so is the conclusion. Let's look at that. I highlighted it here. It's a valid argument. What row are the premises true? There's this row here, so it's a valid argument. Let's put it on the board. So take a minute. Really look at the truth table. Make sure that, right, verify every case where all the premises are true. All right, it might be a little hard to read here because, right, the main logical operator is bolded here, and here's the conclusion. Is there a row where all the premises are true and the conclusion false? True, false, so not all the premises are true. True, false, false, true, not all the premises are true. There's one row, this row here, where both premises are true. On this row, is the conclusion true also? Yes, absolutely it is. All right, let's go over it the other way I suggested. Let me just write this down, then I'll full screen the video. So we have premise 1, if not L, then either J or L. Premise 2, not L. Conclusion, J. Okay. This light source up here is a little bit annoying, right? Like if I move away. Okay. So here's our premise 1, here's premise 2, here's the conclusion. Why is this argument valid? Well, roughly what we have is if not L, then either J or L. But we have not L, so we know not L is going to be true. And so the consequence of not L being true is either J or L is going to be true. Can't be L because not L, therefore J. That's kind of my informal sketch of why this argument is valid. So what I said here is that what we should do is conjoin the premises using an AND. We have a conjunction here. Then I put my conditional statement, and we're going to do this truth table and see what happens. Now we only have 2 atomic sentences, which is good. We're not going to end up with a giant truth table. Let me add a bracket here just to make sure it's perfectly clear what we're doing. So what I'm saying is that if these premises are true, then this conclusion will be true. And that, let me get back in frame here, that should be a tautology. That's my theory. If premises, then conclusion. And I'm going to check this with the truth table. It's a pretty complicated looking set of sentences, but remember, we only need 4 rows because we only have 2 atomic sentences. So let's work through it really quickly here. So we have L and J. So why don't we go T, T, F, then we have J or T, F, T, F. Now all the other atomic sentences are going to have to mirror what we just did, no matter where they are in this complicated sentence of SL to make up the full truth table. So we should have true, true, false, false for L. Again, here's another L, true, true, false, false. And finally we have J, which will be true, false, true, false. Now the main logical operator is the if-then. So we're going to do that one last. What should we do next? Well, we should work on what's directly operating on the atomic sentences. We have a couple negations. Let's do those. False, false, true, true. False, false, true, true. Can we do this and yet? We can't. We need to do what's inside over here first. Can we do the if-then? No, because the negation and the disjunction are working together for the value of the if-then. So the next one we should do is here. J, either J or L. True, 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 false, which is what you'd expect. And now these two, the negation and the disjunction, are going to combine to give you the value of the if-then. Now the if-then truth table is pretty simple. It's always true unless TF, unless the antecedent is true, the consequent false. So we have false, true, true, false, true, 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 true. This T is unambiguous. True, false. There it is. False. Now we have this is a bit of a longer truth table because you've got to kind of work it out mechanically, but that's fine. Now we're in a position to do this and here because the if is going to talk to the negation to give you the values of the and. So we have true, false, false, true, false, false, true, 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 false, true, false. Okay, so the and only has one T, which is over here, which is kind of interesting. And now we are in a position to do the main logical operator. And boy, I hope I didn't mess this up because this is like 5 minutes of setup. I'm going to have to like go back and make another awkward cut again. But I don't think I made any mistakes. So, is this statement going to be a tautology? This is an if-then statement. Antecedent is false, so the if-then is true. False, false, true. True, true, true. False, false, true. So there's no case where the if-then is going to be false. In other words, the statement if premise and premise, then conclusion is a tautology. In other words, the argument has to be valid. There's no case where you have true premises and a false conclusion. Now this extra step might seem a bit silly because all we had to do in the last case was just find the one row where the premises are true, and then see if the conclusion was also true. That's correct, but then you have to kind of look at them. This is a more mechanical way. You do the full truth table, you find out that it's a tautology, you know it's valid. Or you can negate the whole thing and find out it's a contradiction, and then denying the entailment, denying the conditional is a contradiction, so you see that it's also valid. So these are a couple of ways to find out whether an argument is valid using only sentential logic. Now we're working entirely within the confines of sentential logic. What we haven't done yet is taking an argument in English, translating it to SL, and then testing for its validity. We're going to get there. Right now, what we've shown to be able to do is using truth tables only, find out whether an argument is valid using only the kind of internal framework of sentential logic by working out the truth table. Right. Here's the conditional validity test we just did. You see that there's a tautology here. There's a negation here. Right. So this might be a bit more legible than how I worked through it over here, but I'm glad we worked through it because you kind of see how we have to work outwards to the main logical operator. Otherwise, pause the video, have a look at that truth table, and understand why this negated conditional validity test can tell you that an argument is valid in SL or not. All right. Did you pause? You had to look at it? Awesome. Great. Now it's your turn. Show that the following arguments are valid using a truth table by showing the corresponding conditional is a contradiction. Or, well, actually, you can just show that the corresponding negated conditional. Can I edit this while I'm here? Oh my God, I can. Showing negated conditional is a contradiction. And this one should be over here. There we go. That looks perfect. You can also just show that the conditional is a tautology. That's fine. The idea is I just want you to stop and prove that these are valid arguments. All right, so pause the video. You really need to work through these 5 examples. I'm telling you they're valid. I'm not expecting you to show whether they're valid or invalid. You know they're valid. Just prove it. All right, how did that work out? Worked out okay? I'm going to do one of these, and then we're going to move on. I'm going to stop the video, then we're going to have the next part of Chapter 7. Okay, let's just do one. Which one should we do? How about either P or Q, not Q, therefore P? That one's pretty easy. Okay, let's erase this. So the premise, let's just write the argument in standard form over here. What we have is premise 1, either P or Q. Premise 2. What was premise 2? Was it not, can't believe I forgot. Not Q, therefore P. It didn't really matter, it doesn't matter which side you did. Not Q, conclusion, P. So, we can do the full truth table, we can do the conditional, the negated conditional check. Why don't we do the conditional? I like that version. So we have either P or Q, and not Q. These are my premises. Now, when I made this conjunction, this and statement, I put in brackets to make sure that we understand that either P or Q, and not the case that Q. Then I'm going to put in my arrow here for the conditional, add some extra brackets, make sure we understand this chunk is going to be talking to the conclusion chunk, which is P. Now, I would expect this to be a tautology. Now, I could do the full truth table, but the fact is, this video is half an hour long, and I'm getting a little bit lazy. I'd like to stop recording, have lunch, and then get back to it. So what I'm going to do here is a shortened proof by contradiction. I'm not going to do the full truth table. I've done this a couple times already. Maybe you'll kind of get the hang of what I mean by osmosis. What do I mean by proof by contradiction? I want this to come out to be a tautology because it's a valid argument. If premises, then conclusion should be a tautology. So what we should ask isn't, is it always true? What we should ask is, can this be false? So I'm going to go, false? Question mark. That's my hypothesis. I'm going to assume that this is false. Now, when is a conditional false? There's one case, when the antecedent is true and the consequent false. So I know that the value of P is going to have to be false for this to be false. So that's the way the truth table of the conditional goes. What's the next main logical operator? What's the next operator in line that needs to be true? This and. This and needs to be true. We need true, false, right? True, false, false. That's the setup we need to show that this isn't a tautology. But of course it is a tautology. So what we're looking for is a contradiction somewhere. So for this to be true, both sides have to be true. All right? So this or has to be true, and this not Q has to be true. Now, I'm not saying Q has to be true. I'm saying not Q has to be true. And if not true has to be Q, if not Q has to be true, then Q itself has to be false. I've been talking for like 5 hours at this point. So the value of Q is false, right? Because not Q is true. What's the value of P? P is false. I've already established that P has to be false in order for this condition to be false. So I'm going to throw in that value here. P is equal to false. Now, we run into a contradiction here. What is the contradiction? Right here. In order for this conditional to be false, P, the atomic sentence P has to take the value false, and the atomic sentence Q has to take the value false. But if P and Q have to be false, then either P or Q has to be false. Right here. Now we have a problem. Because for this conditional to be false, the premises can't all be true simultaneously. One of the premises has to be false. So there's no case where this can take the value of F. We tried working it out, and the logical conclusion of this conditional taking the value F is that we have a contradiction. Think back to Minesweeper, right? What I have is a little bit of information. I inputted some information to the system. What information did I input? F. In Minesweeper, the system gives you numbers that represent where mines are, and then you work out the logical consequences of the information you've been given. So the information I have is that if this is a valid argument, this conditional is going to be a tautology. So I say, well, let's see if the opposite is possible. Could this possibly be false? So I inputted the information F. From that F underneath the arrow, I can make logical deductions. If this arrow is F, then this must be true and that false. If this is false, then P is going to have the value false throughout. If this is true, then Q is going to have the value false throughout. But if P and Q are false, then this conjunction must be, this disjunction, this OR must be false. If the OR is false, you can't have true premises and a false conclusion because all the premises have to be true. In other words, we have a contradiction because the OR here has to be simultaneously true and false in order to have true premises and a false conclusion. So this shortened truth table, I checked to see whether or not the conditional could possibly have F, and it can't. Because if I work out the logical implications of assigning F to the conditional, I get a contradiction. So that's a nice short way of proving that this argument is in fact a valid argument. So, getting back to here, I encourage you to use any of these methods to verify that these arguments, are indeed valid. It's particularly useful when you have a lot of sentence letters and you don't want to do like an 8 or 16 row truth table. That's too much work. So, for example, on this argument here, right, which is if A then B, if B then C, conclusion if A then C, right, you could, for example, use a shortened truth table. So, get on it. Work hard. I believe in you. You can do the thing. All right, thanks for watching.